NanoHub U, online instruction.
Hey everyone, welcome to lecture 415. So in the last lecture, we just explained the basic physics of thermal transport, and then we actually mentioned the specific connection with optics, which is that we can use absorptivity to calculate emissivity, which tells us about radiative thermal transfer, and we said that in some regimes, that's the most important thing. But first, we're going to actually look at convection and conduction, because we said in a lot of typical situations, just in the household and so on, then actually those are the dominant heat transfer mechanisms. So we need to have those first before we go to radiative heat transfer. And so if you recall, we had actually shown that you can combine conduction and convection into a bunch of linear algebra problems. And if we write down the matrices in kind of a very simple form, then you can actually write it like this. And so this is very similar to what we had previously. And so you have basically this C matrix, which is a surface integral of these basis functions, which are, of course, dependent on your choice of finite element grid and so on, times the first derivative in time of temperature. And then you have these K and H components. K we'd already talked about, and then this was directly derived from conduction. And then there could also be a convective term, H. So this is basically being added to this K for conduction. And then this Li is a bunch of boundary conditions for basically the volumetric generation of heat or dissipation of heat plus the convection on that surface. And if you want to go through this in a lot more detail, then please look at Peter Crystal's book on the topic, which is freely available online, in chapter 6 especially. And you can go here to download the book. You can download the code right here. And there, he also has a course webpage. You can download some of that information as well. So just to briefly explain how this works. So this is a MATLAB toolbox. So this assumes you have MATLAB generally. But of course, if you don't and you decide not to purchase it, then you could also use Octave. And Octave, of course, is a freely available clone of MATLAB and has many of the same functionalities. So in any case, but from now on, I'll just assume you're using MATLAB. So if we perform a 1D meshing routine in this sort of toolbox, then you can actually see that the approach is fairly straightforward. So you would have to have some sort of strategy about the dimensionality of the system in order to create nodes and then make connections between the nodes. And of course, when you create the mesh, usually the goal is to have a relatively sparse matrix here. In this case, it's just a 1D problem, and so you're just spacing them out more or less evenly. Okay, so you can see X is just increasing linearly over space, and then you actually create like a bunch of the connections, and then you can see here, this is just saying like nearest neighbor connections. So this is good because it's going to be much easier to solve and invert these kind of problems with very sparse matrices than if the matrix was densely populated and everything was connected directly to everything else. So once you have this sort of mesh set up, then you can create a finite element block. And then this finite element block is basically setting up your structure for various types of solutions. And so in this case, we would pick the kind of problem that we had like a while ago, which was related to the mechanical problem, where you have a tight string, there's some sort of tension and there's gravity on the string, and then you're trying to look at the dynamics of the string, if it's time dependent, or the static equilibrium of the string, if it's not vibrating, if it's just in a steady state. And then you have to define the integration rule that you're using to solve it. And then you create basically a field with the structure of the geometry. And here the dimensionality is specified, so that's also very important. And then once you create this geometry, then you would create a W, which was like your solution for the system as well, using this clone command here. And so once you have that basic setup, like kind of the core of the problem, then you have to apply the boundary conditions correctly to the problem. And so this is actually showing how you can create these. Here, basically, we're just specifying like a prescribed value of 1 at some position and then a value of 0 at the other side. And so this is setting the boundary conditions explicitly, the set EBC and apply EBC terms. And then W is now just generating like the equations that are associated with those boundary conditions. And then you have to assemble all these equations from kind of the core and the boundary conditions together. And so this creates like a dense system matrix. Of course, this is the most general approach, but more, for higher performance, you would probably want to use a sparse matrix if possible. Here you're assembling the elements of the stiffness matrix together. Here you're actually loading the structure, and then you're starting the equation to basically iterate over time, and then you're assembling the body loads, and then you're calculating the solution matrix. So that's basically how it works. So of course, that was a whirlwind tour, but this, although applied in this particular example to mechanical system, just because it's very simple, could also apply to thermal models and many other models. And so in the next lecture, we'll talk more about like what kind of solutions can you get from this sort of approach.